So the title of the webinar, Sustainable Cooling Technologies for Preservation of Crops, is the first webinar session, and this is a joint effort of the Nigerian Store Products Research Institute in Ilorin, the company Kotutu in Lagos, the solar company Faesan, based in Germany, the company Solar Cooling Engineering, which is an engineering company, and under the brand SelfChill. I'm going to tell you more about that in a second. And just to mention that this webinar is part of the EES project, which is supported by the German Federal Ministry of Economic, as part of a program that is supporting us to promote the use of solar energy for refrigeration in Nigeria. So we are very happy to have this support. We are very happy to be here today with you. And now I'm going to the next slide so that you can have a look here. What is the session of today, and what will happen also in the second session that will take place in 2 months. So today, we are going to start with the requirements of agricultural produce, because we think this is very important to get the first motivation. Why are we willing to do cooling? And then, of course, in the second part, why we want to do it with solar energy, what are the opportunities we have? And because I guess most of you are aware of how solar systems work, I would like to focus today a little bit more in the refrigeration machines, how a refrigeration machine works, how can we do out of solar energy, cooling energy, so to say. And I would love to make sure that this is understood today, because after lunch, that will be between 12 and 1 o'clock, we'll have 1 hour lunch break. We'll have a look to the components. So we'll have a go through all the different components that we have in a solar cold room. We'll have also some pictures and the samples of solar power cold rooms that have been installed. And we will have a very brief overview of what is the design process of designing a cold room. But this part on the design, this we will have in a more extensive way in the second webinar session that will take place in March 2023. We will keep you updated so that you can also do the registration. And on that day, we will focus a lot on the calculation of cooling demand, which is very necessary to be able to design ice storage, batteries, PV, and so on. And we will show you also and provide you access to a design toolbox that we have in Excel, so that we can do the design process of a solar cold room with a computational model with our laptops. And we will also show you some cooling systems, some other cooling systems. This is going to take place in around 2 months. And today we are going to focus in our session 1, which is going to get us through the fascinating world of solar cooling. And we can be very happy, and we are really happy. We will also be in Nigeria this year, having a face-to-face training at NISPRI in Ilorin, and also some field visits that will come this year. So be in touch with us after these 2 webinars. Very exciting activities will come to Nigeria. You might be asking yourself, what is SelfChill all about? So SelfChill is our brand. It's the brand for modular cooling solutions powered by solar. And this is more an approach than a technology. Why is it an approach? It's an approach because it's promoting the local production of solar cooling systems. Those cooling systems are modular and are especially designed for local production. That's why we are a couple of companies involved in this from Germany. You see here the company Solar Cooling Engineering, that is a spin-off company of the University of Hohenheim, where the self-chill approach was born. From Germany, we have the solar company Faesan, that is the distributor and integrator of the systems. Is distributing all the key components that are needed, also with kits for connection cables, PV panels, and so on, so that the installation and the local production is very easy. And in Nigeria, we have very two important institutions. We have the Nigerian Store Product Research Institute, NISPRI, which is since already 3 years doing research on solar cooling solutions. And as many of you know, has already its own solar power cooling solution based on the self-chill approach. And our distributor in Nigeria, the company Ekotutu, that has already installed one cold room in Benin City under the self-chill approach, totally local produce made in Nigeria, and is currently also planning the second cold room in Lagos. I will let you know later on a little bit more on this. Before we go into the material of solar cooling, I would like to let you know a little bit more about our purpose, about our vision. Why are we doing this? Why are we doing solar cooling in Germany? Why are we cooperating with Nigerian institutions to promote solar cooling? So one of our main objectives and purposes are the awareness creation, how interesting it is to use solar energy for refrigeration. When we have refrigeration needs, it's also because if it is warm. So the use of solar energy for refrigeration match very well, because when you have the demand, you have also the energy availability. So we believe this is the best way of doing refrigeration, is using solar energy. That's why we are promoting that. But we think it's exactly so important also to promote the local production. We cannot be sending or having cooling solutions that are designed in a country and are going to work in another country. Even a solution that is designed in Lagos might not work in rural areas in Nigeria. That's why it's very important to have technologies that can be adapted to the local context. And this is what we are promoting with our cooling solutions that are suitable for local production. So we are talking always about solutions that are made in Africa. We are talking about a value chain of about, or added value of about 70%. So 70% of the materials are a local source, so that the solutions are made in Africa. We provide engineering support and trainings. This is part of our purpose, to provide the needed support for this local production. And what is very important for us, sustainable cooling. So nowadays sustainability has become very important, and this is not only coming because of solar. Solar is sustainable, it is true, but not only that, we need also to take care on the refrigerants that we are using. So we use natural refrigerants with low global warming potential that are not damaging the climate, and this is not always the case for all refrigeration machines. We'll see on a slide on that later on. What we also promote is thermal storage. You can see here. Why not using ice storage instead of batteries, or a mixture of both? So this is also a part of our vision. And what we are recently also starting is natural insulation materials. So the insulation materials, like what you see here for the sandwich panels of a cold room, can be also become more sustainable by using other kind of materials that are more climate friendly than the actual or the current sandwich panels that are on the market. Okay, so now I would like to make sure you are with us. There is already, I think, one question going on. Is the system self-chill or getting chill from solar? It's a good question. Self-chill means we are doing we are chilling with self-made products. That's why the brand Self-Chill. So self is not that the system is chilling itself, is because we are doing do-it-yourself systems, so to say, for local production. So the Self-Chill systems are run by solar energy. So we are following here. Now I would like to have here a question to see if everybody is here with us. So let's go for that. My question is, are we together? So I would like to get your answer. I really want to feel that you are here. Please don't hesitate to make your comments. Say, I like it, I don't like it, I don't understand this. Please repeat this slide and so on. Or I didn't know that. Interesting. Can you repeat something, please? We are here for you. We are just not talking. We are here for you. We are listening. And thank you very much. This was a very fast reaction from your side. This is then giving us the feeling you are following us. Please use the chat function and put your comments. Let's continue. This is going to be a very exciting time. And it is wonderful that we can be connected online, being in Germany and you in other places of Nigeria. Before we continue, to let you know, we are talking today about solar power cold rooms. Okay, so it's about a system that has somewhere PV panels, and somewhere we have a insulated room, and from somewhere we are getting cooling energy, right? So here you see an example of a cold room with a heat exchanger that is delivering cooling energy. And then you see here a box. We will learn later on that this box is a thermal storage system. Okay, so we are talking about walk-in solar power cold rooms. How do they work? We need always a place where we have cooling. That's clear. We need a ventilator. We need to keep on moving the air. We might need humidification because of the products, and then we need the products, and we need to distribute the air for the products in a very good way so that all the products or the agricultural produce feel the cold air, and then we cool down that air again. Okay, I think that's clear for everybody. Before we get deeper into detail, here you see an example of our solar power cold room at a marketplace, and we would like to know, before we are planning a solar cold room, we would like to know what we need to consider. So we need to consider the location. Where is it going to be? I have put it here also in yellow, what I think is very important, also the business model, right? As you can see here, what are we going to do with the cold room? Are we storing products from the market? Are we storing products to sell them later? What are we doing exactly? What is our business model behind? That's crucial. Then we need to consider which types of cold storage are we going to use. Are we going to use one chamber, two chambers? Are we going to use solar PV, or do we have access to the grid? Do we want to do thermal storage, and so on? And right after that, the next thing we need to do, and this you will see at the end of this webinar, and especially also in the next webinar, the estimation of the cooling demand and how to deliver the power. And I can tell you in advance, it makes a huge difference how you use the cold room. It makes a huge difference if you are entering the cold room half a ton per day or 1 ton per day. That will make your cooling demand much higher, and therefore also the amount of PV panels that you might need, the investment you need to do. Something else I want to let you know, because this is a solar power system, and the ambient temperature has also an effect on the cooling demand and on the efficiency of the refrigeration machines. The location where you are is going to be also crucial, depending on the city where you are. If it's, for example, in the seaside with very warm temperatures, you will have higher cooling demand, less efficiency, more cost, more PV panels, and so on. Very important to figure out at the beginning what are we going to do with the cold room, and where is the cold room going to be installed. But why cold storage? You know, agricultural value chains have been working for many centuries without cold storage. So why do we want to do cold storage? We might like to save nutritional value over a longer time, is clear. Minimize mass loss, slow ripening. I think those are ideas that might come to your mind. Feel free to enter into the chat other ideas that you might have. And then at the end of the day, we are controlling the growth of microorganisms. So if you have a look to this diagram where you see microorganisms are growing faster, the hotter the temperature is, then the question to you will be, what will be the best cooling temperature for the products? Is it then as minimum as we can do, yes or no? Please write it on the chat. I don't have any question for this, but you could start thinking about it. Is it going to be then 2 degrees, like very cold but without freezing, or what is your feeling? Please write it on the chat so that we can get some ideas also for everybody to follow. And in the meantime, I have to tell you, there are good things of cold storage, but there are also bad news of cold storage. Sometimes you put your produce in the cold storage and then you get it after a while, supposed to be perfect, but then you open it and the quality is not good. So there is some knowledge we need to have under control. And this is the first part of the webinars today, because with agricultural produce, with fruits and vegetables, we are talking about a living plant, right? This is not a dead plant that you just need to store. This is the case of meat, fish, and milk. In those 3 products, is not a living plant, so we need to keep it at lowest temperature. But with living plants like vegetables and fruits, we need to consider in other things that are going on. So we have, from the one side, physiological processes going on. The fruit is growing, is getting bigger, is ripening, and the other processes are metabolic changes. The taste is changing, the color is changing, and all of that is what makes the post-harvest quality, and it what makes our product become tasty or get the maturity suitable for the market. Let's have a look to this. What's happened? The product is somehow ripening on the plant, on the tree, and at some time we have achieved a physiological maturity. This means if we take the product, we harvest the product, then the product can survive and keep on ripening over the time. But not all products are like this. Only climateric products have this property of being able to ripe after harvesting. They are very interesting for us because climateric products are able to get harvest before. For example, here already. Let's have a look if this is working. We can harvest here, and then we can store them and control the ripening so that when we take the product out of the cold storage, we can get the commercial maturity we want to have. And this is very interesting. That's why I would like to do here at this stage, open a new question. Just give me 1 second if I'm able to get into there. And we are talking here about business opportunities. So if we have learned this, there are some products can do this. Let me see. Now I have it, sorry. What are the business opportunities with cooling? Yeah, what do you think is the best? I have set 3 examples. I would like to know which one you like most. So what is the first one that comes to your mind? The first one is saving the product from spoilage. So we have a mature product, we are in the market, we want to save it because we want to be able to sell it tomorrow and next week. The second one is getting the best quality at the right time. This will be, no, I do the harvest before, like you can see here. And then I have the best quality or I control the ripening so that I have the best quality when I come to the market. So I have my cold storage, then I take my products, I control the ripening depending how much products I would like to sell. So for this, I need somehow a market intelligence to know, okay, how much products I'm going to sell next week so that you can start controlling the ripening. And the third one is get access to higher prices. Imagine you can store mangoes over a longer time of period because you have harvested them before. Then you have them for much longer time than others, let's say farmers without cooling access. And then you can sell mangoes out of season. And this is going to be able to sell the mangoes at a higher price. Also a very interesting business model, right? So we have 3 business models here. Please let us know what is the one you like most. So it seems everybody voted already. 21 persons voted. Thank you very much. Let's have results for this. Can you see the results? Okay. So it seems actually most of you said the saving produce from spoilage is like the most interesting business model for you, or the one you like it more. Yeah, this is like a little bit a reactive mode, right? So you have your products, you are not selling them, you need to store them, right? This will be the case for a cold room at a marketplace. So very good. It's a very good business model. Then we have 17% of the attendees today thinking that a good business model would be to get the best quality at the right time. And I have to say, this is the most used business model for cold storage rooms in big storage room and big storage facilities, because they have the aim not to be reactive, but to be proactive. So you harvest the products before you have them on the cold room, and based on the temperature, you will control the ripening so that once you come to the market, you have the best quality. This is done, for example, for bananas. They are harvested before so that during transport to the final markets, they get the ripening process, and at the end at the supermarkets they can have the final ripening process, so they come to the hands of the customers under the best quality they could have. So it's not saving them from spoilage, it's having like a higher intelligence to get the most out of it. And this, I have to tell you, is one of the most promising business models of cooling, with higher scale. And then 30% of you went for get access to higher prices by storing the products longer. So this is making use of seasonality, right? What about if you can be selling mangoes all over the year, for example? Yeah, this is amazing. Then you can have access to higher prices. And this is everything able or possible with help of cold storage. But as you are seeing here, you need to consider other things. You need to consider the development of your product. You need to consider the ripening process. You have to understand this very well, right? If you don't understand this, you won't be able to make use of this business model. Also, we need to understand the water loss. What is the humidity that we need? The respiration, how can we stop this to make the product be able to last longer? Avoiding mechanical stress, of course. Ethylene, I guess most of you have heard about this. So I was talking here about ripening process. We need to understand how it happens, water loss, respiration, ethylene gas. We have a slide for this, and we need to understand very well chilling injury, which is something very interesting. I mean, most of you are experts on this, especially the colleague from NISPRI, but not all products like to be cold. Let's have an example here. For example, the bananas, if you store them at 10 degrees, then they don't change so much the color. You can store them for a couple of weeks, but if you go for 5 or 0 degrees, you can see here they change the color. So we have here metabolic change. which is causing a disorder, in this case only on the color, because the taste might not be so bad, but nobody is going to be willing to buy your bananas if you are storing them like this. Rather, you will sell them like this, because this is more a natural development of the bananas. The same happens to tomatoes. They don't like to be so cold. Here you have also an example of chilled tomatoes that have a chilling injury. So we need to understand very well what is going on with the product, what are the optimal temperature conditions and humidity conditions that are required from the product, and we need to find a balance here between slowing the ripening. So we want to decrease the temperature, but not so much, because if we have low temperature, we might have chilling injury. So we have to find our balance. And to find our balance, we need to make use of scientific data. We need to ask researchers, and that's why we have the Nigerian Store Product Research Institute, because we need to know what are the best conditions for our products to ripe in the best way and not to have chilling injuries. So to sensibilize you with this a little bit more, I would like you to see this diagram where you see here the shelf life of the products depending on the temperature. So let's have a look here to the banana. So we saw 5 degrees they don't like, 15 degrees they are good. Yeah, so let's have a look here. Look, if we are at 15 degrees with banana, we can go up to 20 days shelf life. Very nice. Papaya, for example, has another optimal value. And you see with banana, like if you go to 12 degrees or you go to 17 degrees, they deal well with this, as you can see here. But this is not the case for all products. Let's have a look to avocado, for example. Look what's happened. The optimal temperature is here about 7 degrees. 7.5. If you move a little bit, you go to 5 degrees, then you don't get access to the, you have chilling injury, and then they spoil a little bit faster. So at 5 degrees, for example, you get the same shelf life than at 17 degrees with avocados. So this is a very sensitive product. Avocado likes to be at 7.5 degrees, and it doesn't allow to have 2 degrees more or less. It has to be exactly at this temperature. That's why it's so important to make use of research data so that we can understand our product very good. So my question will be, can we store avocados and banana in the same storage room? Let's see, if avocado likes to be at 7.5 and banana doesn't like to be at 7.5, we have a conflict. We cannot store them in the same chamber. We might need a second chamber at another temperature. This is very important. That's why it's important to deal with these kind of tables that are letting us know, okay, the temperature of banana is like this. Also the humidity, for example, fruits like grapes, they don't like to be so humid, but banana likes to be humid, like tomatoes and others, because otherwise they will dry, and we don't want to have a dry product. But if we have a lot of humidity for products that don't like that, then we might get some fungi development going on. That's why it's very important to figure out, are the products compatible with each other, and what is the optimal temperature, the optimal humidity I need to have there. And not only this, we have also, as I mentioned before, the problem of ethylene gas. What is ethylene gas? Most of you might know about this. Ethylene gas is the communication between products, between fruits, between vegetables. Once a mango is in the tree and is ready for ripening, it emits ethylene to tell the other mangoes it is time to ripe, so that all of them ripe. And not only this, there will be also this ethylene gas coming to the neighbor tree, so that the mangoes of that tree start to ripe also. Very nice for the nature, but not so good for the cold storage rooms. Because if you, for example, put a product that is emitting ethylene together with a product that is sensible to ethylene, then you will have a negative effect. have an example here at what's happened with cucumbers. You see here cucumbers without ethylene. They are very sensitive to ethylene, but don't emit ethylene. So after here 9 days, the cucumbers are doing well. They have a good quality, no problem. Now let's put apples together with them. This is the sample here with ethylene. Apples, mangoes, and other fruits emit a lot of ethylene. What's happened? They are together in the same cold room. The temperatures are okay for both. The humidities are okay for both. But the problem with the ethylene is that the ethylene is damaging here the cucumber. So after 9 days, have a look here. What's going on? We have a spoilage. We have a damage of cucumbers because of ethylene. The problem of ethylene is you don't see it. Yeah, if you don't see it, how can you know it? It's impossible to know it. That's why we need to inform ourselves what's going on with temperature, humidity, but also ethylene. There might be solutions having separated chambers or using plastic bags, like you can see here with the bags. What's happened? No ethylene can go inside the bag, so those products are protected. But what is happening there? Because the products are having respiration, then they are going to consume the oxygen in the bag, and then you will have a lot of CO2. So you need to know if this fruit is going to be able to have so much CO2 and not be CO2 and not being affected. That's why we need to know the sensitivity of the product also to CO2. So we have mentioned already temperature, humidity, ethylene, and CO2, right? This is what we need to consider, and no worries. You see here also a table of which products are sensitive to ethylene, which one not. You could use a book, but we are lucky today. There are other things. We have internet, we have our laptops, we have our mobile phones. So there is a fantastic app from the University of California. Anna, perhaps you can put the link on the chat so that everybody can open it. And this is really wonderful. You can use it with your laptop, or you can just install it with your mobile phone. You download the app, and then you see there all different products, vegetables, fruits, even varieties. You see here, for example, different varieties of apples. This is really wonderful. You have to have a look to this. And what's happened if we go, for example, for grapes? Let's go for grapes. Let's inform ourselves what grapes, what I need to know from them if I want to store them. So here we are getting information. Best storage temperature, yeah, around 0 degrees is recommended. What about the humidity? Yeah, we see here this humidity, even though I told you from before they don't like it so humid because they're avoiding fungi, but this is the information we get here. Then we have also the rates of respiration. This is also important to know, yeah, if they are going to emit CO2 or not. Then we have here the response to ethylene. Yeah, are not very sensitive to ethylene. Wonderful. We can store them with products that emit ethylene, like mangoes and apples and so on. And then the response is to control atmosphere. Yeah, it is not recommended to have this to have these limits of CO2 because the grapes will let me read it again. Yeah, so these values are not recommended during shipment for the reasons here. So you are getting this information also of every product. And then what I like also a lot are the disorders. So for example, something that will happen if you are dealing with grapes in storage rooms is that you might have contaminations coming from the field, and then under high humidity, you then see what's that you had fungi contamination at your product and so on. So you can inform yourself about this before, so that you can understand what are the best conditions for a certain product. So we recommend you a lot to install this app into your mobile phone. And we are finalizing now the first part of the of our webinar today, dealing with agricultural produce. I hope you enjoyed that part, and now it's going to be even more exciting because I guess most of you connected today because you want to learn or you want to hear how to run cooling systems with solar energy. You are seeing here a typical refrigeration unit on the side, could be an air conditioning system, and you are seeing here a PV panel. So we are coming closer, but that's not the only way of doing solar cooling. So if we consider that we have solar radiation and we want to use it for cooling, I have to tell you before going here, you might like to consider evaporative cooling, which is even free of energy. This means you have a material that is wet, and because water is evaporating, you have a cooling effect. So we need to use this every time we can, especially in dry ambient conditions. You can make use of this in a very productive way. So you might have heard about evaporative coolers. But in the past, solar cooling was done with thermal modules, doing heat out of solar energy and then using machines called adsorption or absorption machines. You might know them. They had been used for high-scale solar cooling, and they don't use PV panels. They use solar thermal. We are not talking about them today, but it was important for me to mention them. Or we can use photovoltaic panels. And before going to the vapor compression heat pumps, that is going to be the focus today, I would like to let you know about thermoelectric Peltier elements. You might know this. This is actually used in a small cool boxes, yeah, that have a fan in the inside and in the outside. They look like this, yeah. You have like a Peltier a module, and then you apply a voltage, and then you get a cold surface and a warm surface. Very interesting, not so efficient for medium scale, for higher scale, but for small cooling boxes might be the best option for you. And the focus of today, our vapor compression heat pumps. This is actually the most used cooling system, conventional refrigeration systems. As you know, they always have a compressor, and they are compressing a refrigerant and are producing the cooling effect. They are called, by the way, heat pumps. If you don't know why they are called heat pumps, no worries, you are going to understand why they are called heat pumps today. Before we go ahead, let's have a look to the importance of climate-friendly refrigerants. So I just told you a refrigeration machine is using a refrigerant, and we are compressing this refrigerant and are working with this. And this refrigerant, not all of them were climate friendly. You remember the ozone depletion we had in the last decades. And nowadays we have a problem with the global warming potential of the refrigerant. So the most used refrigerants, for example, for air conditioning at the moment are here, yeah, R410A. R12 is not anymore permitted. I don't know if you have this much in Nigeria. You will find also R32. R134A is used in vehicles and in most mobile applications. But as you can see here, they have a quite high global warming potential. What does it mean? It means, you can see it here, global warming potential, carbon dioxide equivalents. It means if you have, let's go here for this one. If you have 1 gram of R410A, then it's like having 2,000 grams of CO2. So once the refrigerant is coming to the atmosphere, then you have 2 kg CO2 equivalent per gram of refrigerant. And I can tell you those systems might have between 1 and 3 kg of the refrigerant. So this means you are going to have 2 to 6 tons of CO2 emitted to the atmosphere. And this is a lot of CO2, a very bad impact into the climate. I can tell you this is about driving with your car about 20,000 kilometers. So this is a lot CO2 that we are emitting only because this refrigerant came to the atmosphere. And you know, these cooling systems normally lose a little bit of gas, so they have to be refilled and so on. So we have to be aware of that. And we cannot really say a solar cooling system is sustainable if it uses one of those refrigerants, because we are saving, we are being efficient by using solar, but not sustainable using the refrigerant. So that's why it's very important to use natural refrigerants. What is a natural refrigerant? It's a refrigerant that is in the nature. It's not a chemical. And we, for example, use here R600A and R290. This is isobutane and this is propane. They have a very low global warming potential. So it doesn't matter if this refrigerant is coming to the atmosphere because the impact in climate is very low. The problem of those refrigerants is they are explosive, but I tell you in advance, this is not a problem in medium scale systems. It might be or is a problem in higher scale systems, but for air conditioning, cold rooms, and so on, this is not an issue because the amount of refrigerant inside the system is not big enough to have a explosive mixture inside the cold room or inside the house. So no problem with this. We have also low quantities of refrigerant, lower than the other ones. So no problem, but please be aware of global warming potential of refrigerants. There is one question. Cecilia, you are now allowed to talk and make the question. If you have one, we saw your hand rising. Oh, hold on.
Yeah.
No? Or you can write it on the chat. In the meanwhile, please write it on the chat, and there is also the possibility to talk. So you raise your hand and we'll give you access to talk, so that you just need to unmute yourself and then you can make any question. There is one. There are two questions here. Aside from the global warming potential of the refrigerant, do you also consider the ODP? Very good question. Yes, of course, this is a must. And I have to tell you, all refrigerants here, I think besides, not even this one, they don't have ODP or the ocean depletion potential. So this is, of course, I mean, I think all of them are already prohibited, at least here in Europe. That's why we are not even talking about this, because this is a must. Yeah, if they are not yet prohibited, some of them in your country, they will be prohibited. But I think even in Nigeria, they might be already prohibited. And those ones, they will get also prohibited with the time. So yes, of course, very important point. Thank you very much. What is the difference with R608? Well, there is a difference on global warming potential, yeah, here between 1,400 to 3. This is clear for everyone. The other difference is that they have different working pressures and so on. So you cannot use the same compressor. You cannot use the same fridge. You need to change the fridge, the compressor, and so on, because they work at different pressures, different condensing temperatures, evaporating temperatures, and so on. So they have like a different thermodynamical cycle. I hope that's answering the question. Besides that, the cost and so on is similar, but it took a while for the manufacturers to change from R134A to 600A. You can have a look at your fridge at home. You might have whether this one, R134A, or this one, R600A. In Europe, almost all refrigerators have 600A in the meantime. And yeah, many solar refrigerators now have 600A or 290. But have a look to that. If you have a solar refrigerator without the refrigerant, then it's not so sustainable. Yeah. In terms of efficiency, natural refrigerants are also very good. Yes. So no problem for that. Okay. So let's go ahead. And coming to a very interesting point, how does a vapor compression heat pump works? So you see here a typical unit. This is normally outside, right? And this unit for air conditioning is normally inside. So the inner chamber and the ambient when we are talking about cooling. So what is this unit doing? Yeah, what is this unit doing? Please let me know in the chat. And what is this unit doing? This unit is providing us cooling energy. This is clear. It's providing us cold air. Okay, and what is happening here? It's making noise, right? So the compressor might be there, and what else? It is releasing heat, right? It is releasing heat. We get cold, warm air out of this. Okay, what's happening here? What else do we have? We have a compressor and we have an expansion valve. Okay, I know most of you don't know yet about all of these components. That's why we are here today. We would like to understand how we can get cooling energy of such a system. So you see here is also a closed circuit, and let me know if I have a question for you. I would like to know what is the efficiency of such a heat pump or such a refrigeration machine. Imagine your air conditioning at home or at your office. What is the efficiency of this? Let's have a look to this. The efficiency of a refrigeration system is measured by the coefficient of operation. What is the amount of cooling energy we get divided by the amount of electricity we have to invest? This is also the definition of efficiency, right? What do I get? Depending on how much I have invested. Okay, let's have a look to this before we continue. Please vote. Can the coefficient of operation, the efficiency of a cooling unit, be higher than 100%? First answer, yes, even much higher, up to 400%. Yes, but only a bit higher than 100%. The third answer will be no, about 90%, but no higher. The fourth answer will be not at all. Please, always below 100%. Efficiency is always below 100%. I don't know how many engineers are today here with us. Yeah, but it's a very interesting question. Please answer. Not answering is not allowed. So we still have so everyone has answered already. Very nice. Okay, thank you very much. So let's have a look to the results. Okay, so most of you say not at all, always below 100%. You cannot see it yet. Okay, you can see it now. Not at all was answered by 60% of all of you today. Okay, not at all, below 100%. Okay, very nice. But there are other dreamers here in the with us today that are saying yes, even much higher, up to 400%, 21%. Said no, it can be even higher than 100%. Okay. And then we have others that said yes, but only a bit higher than 100%. Okay, so the ones answering 1 and 2, they believe that cooling systems can have a higher efficiency than 100%. I'm going to leave it like this for the time being, and we'll have the same question in 5 minutes, okay? And let's see if we get some changes in the answers. Okay, let's continue. Now we are going to try to understand how a cooling system works. So my objective for the next 3 minutes is you to understand how a system like this works. I guess most of you or some of you know it already, and I would like to ask somebody if would like to explain it to the audience. Somebody attending would like to tell the others what's happened with the compressor, what is the condenser, what is the evaporator, what is the expansion valve, and how can we make out of electricity cooling energy. I would like to ask the audience to if you can hand up your hand. Is there any body would like to explain it to us? I would really love to hear it from some of you before we continue. No voluntaries? Not yet, right, Anna?
No, not yet, not yet.
Okay. You still have the chance to speak and get famous in our webinar today. Please feel free. I will really like to hear somebody. Okay, but no worries. I will then try to do it for you. And if I tell you we have a compressor that is compressing a refrigerant, then we are going into a condenser that is condensing the refrigerant and emitting. Can you repeat it? The question at the BG will be if you could explain how a heat pump works in your words. Telling us what does the compressor does, the condenser, the expansion valve, and the evaporator. Adebiyi, would you like to be the one to let us know in your own words? Let me see. Yeah. So Adebiyi, please feel free to unmute yourself and talk. Let us hear your voice.
Okay, am I all heard now?
Yes, you are.
Okay, thank you very much for a very good job. The way compressor operates, there is point of expansion and there is point of compression. At the point of compression, heat is being absorbed. At the point of expansion, evaporation takes place. The evaporation that takes place is what leads, or the expansion of gas that takes place is what leads to evaporation, which causes a low temperature, a cooling temperature to be released into the environment. So the heat exchanger is what is responsible for releasing the heat into the system, out of the system.
Thank you very much, Adebiji. That was a very good explanation. Thank you so much for being the one explaining it. And this is, now we are going to, okay. Okay, very nice. Thank you very much, Adebiji. That was a very good explanation. This will be the explanation you would get also in a physics class, engineering class at university, that the compressor is compressing the refrigerant, then we have some condensing, expansion, and evaporation phase taking on. And then, as you see here in the diagram, we have somewhere like a power going in, and then we have a heat being rejected in the condenser and heat being extracted in the evaporator. So this is where the cooling energy comes from. We are actually not allowed to talk about cooling energy. It's about removal of heat, right? This is clear for everybody. I, however, prefer talking about cooling energy because it's give us at least me give me a better feeling how to explain it. And now I'm really sure that the ones that have never heard about this explanation still don't understand how a heat pump works. And this is the experience we are doing training by training. It is difficult to explain how a heat pump works by this cycle. Yeah, it is difficult because it is quite complicated to understand very quickly how the condenser, evaporator, compressor, and so on works, and how they can reject heat and extract heat and so on. And that's why now we are going to do something interesting. I'm going to stop this engineering class with this thermodynamic diagram and with this condenser and evaporator, compressor, and so on. I'm going to stop this for a while. And we are going to see our faces, and we are going to try to simplify the technology in a way that we can get an understanding on how a refrigeration machine works. So let me stop that. Can you see now my face bigger? Okay. So hello. You can see me, I hope. Yeah. If you cannot see me, please try to see me by clicking somewhere or let us know so that we can change here something. Yeah, everybody can see me. Okay, now let's focus in something simplified. So let's imagine we are not having a refrigerant, we are not having a condenser, an evaporator, and so on. Let's try to have a look to a technology that is simpler than this, but also able to produce cooling energy out of electricity. And this is going to be also a heat pump. So I want to introduce you the concept of heat pumps. Yeah, heat pump is something that is pumping heat, right? So a refrigeration machine is a heat pump, is pumping heat. So we are pumping heat from the outside to the inside, right? So imagine we are here in a room that is want to be cooled down. So imagine I'm now in a storage room that needs to be, or in a room that needs to be at 20 degrees, yeah, because we want to have air conditioning or we want to have some chilly temperatures. And now imagine the ambient outside that we have at 40 degrees, okay? So inside 20 degrees, outside 40 degrees. And now we want to use a technology that is able to cool down the room out of the ambient. So we want to use a heat pump. We want to pump the cooling energy from the outside to the inside, yeah? Or we want to pump the heat from the inside to outside. It depends how you want to see that. Okay, so now try to follow me. We are going to use a compressor. The compressor has to be for a reason you are going to see in 1 second. Let's imagine a bottle, yeah, a bottle like this, yeah, where I put air. Yeah, I put air, so my refrigerant is air. Yeah, I'm not going to use another refrigerant. I'm going to use air. And now imagine I'm compressing this air inside the bottle, yeah? So, or you can also imagine a balloon that we are compressing with our force, yeah? Or you can imagine a compressor compressing air here inside the bottle. What is happening with the bottle? We are getting, what is happening with the air inside? It is compressing. We are putting more and more and more pressure inside the bottle, more air inside, and more and more and more and more. So I'm using mechanical energy. What's happening with the air? Try to think about it. We are getting more pressure for sure. What else is happening? Yes, we are getting also a higher temperature, right? The air in the bottle is getting warm. So now imagine I'm going from 20 degrees to 30 degrees to 40 degrees to 50 degrees to 60 degrees to 70 degrees. I'm compressing the air so much that I'm getting here in this bottle air at 70 degrees, high pressure, 70 degrees. And I'm taking this bottle outside. So I'm taking this bottle outside. So what do I have? I have air outside. Imagine now the bottle is outside, right? Here's the wall. I have air at 70 degrees and our ambient is at 40 degrees, right? So we have hot air at 70 degrees, ambient at 40 degrees. What's happening here? What's happening with the air in the bottle? The air in the bottle is going to be cooled down, right? It's going to go from 70 degrees to 40 degrees ambient. So do you agree with me that the air in the bottle is going to be cooled down from 70 degrees to 40 degrees because we are in the ambient? Yes. Okay, so if you are with me on this, then you are with me that we are taking cooling energy from the hot ambient, right? We are able to cool down air with the hot ambient temperature. We went from 70 degrees to 40 degrees. Very nice, because we were able to take cooling energy from the ambient, or we were able to release heat to the ambient. Yeah, it's the same. Now I'm taking the bottle at 60 degrees with air, compressed air at 40 degrees ambient temperature. And now I have it inside, and now I'm going to expand this air. So now we have here the expansion valve. You see the valve, in this case, is the valve that is expanding my air. Okay, I expand the air. What is going to happen? Release of pressure, right? The pressure is going to drop. And what else? When we were compressing the air, we were having high pressure, higher temperature. When we decrease the pressure, what's happened with the temperature? It decreased also. Ideally, it will decrease also 30 degrees, yeah? We went from 70 to 40. Now we should go from 40 to, by compressing, we went from 20 to 70 degrees, yeah? So now we are going to have the same delta T, ideally. Normally, it's going to be less, but you agree with me, the air here inside, by being expanded, is going to go from 40 degrees at around, I will say, 10 degrees. So now we have cold air coming out of the bottle that is helping us to cool down the room, yeah? Where does this cold air come from? Where does this cooling energy come from? It comes from the ambient. It doesn't come from the compressor, right? The compressor helped us to get pressure, get high pressure, high temperature. Then we decrease the temperature with the ambient, and then we expand the pressure, and at the same time, the temperature decreases even more. So the cooling energy actually is coming from the ambient. Yeah, it's exactly the same cooling energy we got from the ambient that we were able to release to the room. Yeah, that's why the compressor is just helping us to work at different temperature levels, right? By compressing, expanding, we are able to work at a high temperature so that we can get cooling from the ambient. Then we expand, and then we get this cooling energy released into the room, but at a different temperature because we are at a different pressure. Okay, so I hope this is getting clearer for you, that this is a heat pump, right? The cooling energy is not coming from the compressor. It is coming from the ambient because we are pumping cooling energy from the ambient to the room. Okay, so now that we have seen about this, I'm going to share again the slides and have a look again to this diagram. Let me see if I'm able to do it. Yes, here I'm again. Okay. Okay, so was it understandable to you, this explanation? I would like to know, are we following? Are we together? Everybody. Okay, so hold on. Are we together? Everybody understood the concept of heat pump? Yeah, because this, what I explained, is an air compression heat pump. It's not vapor compression heat pump. It's an air compression heat pump. If you have understood this, you will understand everything. Okay, thank you very much. Everybody is here with us. Thank you so much. So now we can continue. So now, why do we need a refrigerant? Why do we need a condenser? What is this all about? Okay, you understood it with the air, yeah, and you saw with the air we needed to go to 70 degrees, right? It's quite high temperature. And the air, what's the problem of the air? The heat capacity of the air is low. We need a lot of air to be able to transport the cooling energy inside. That's why we don't want to use air. We want to use a refrigerant. The refrigerant has a higher density, heat density, and it has also an availability to have a phase change. Yeah. What about if you are compressing vapor? Yeah. And then we are able to condense this vapor while releasing heat, while getting cooling energy, and be able to have a stable temperature. This will be very nice, right? Because then you don't have to go to higher temperature. So let's have a look to this. If we have the compressor here and we are compressing vapor, and this vapor is, so to say, at 50 degrees, and then we are able to cool down the vapor, yeah? Then what's happening? We are cooling down the vapor, but we are at a temperature where this vapor is going to get into liquid. This is wonderful, right? Because in the phase change, we are able to keep stable temperatures, and we are able to get a lot of cooling energy from the ambient or release a lot of heat to the ambient. Very nice, because we have been able to limit a little bit the temperature we had. So that we don't need to 70 degrees, we can be at 50 degrees. Very nice. We don't need to heat up so much. Then we have the expansion valve, and if we have an evaporator, that is actually a heat exchanger, where you are able to, you expand the liquid, and then you are able to get from liquid to gas to evaporate the refrigerant and be at a stable temperature, let's say 10 degrees, it could be 0 degrees, depending on the system. Then you are also able to release a lot of cooling energy into your room, into your device. Yeah, and that's why we use a refrigerant. That's why we condense and evaporate, because we want to have a density of energy. But that's all. A condenser and evaporator is just a heat exchanger. It is no more than that. But because we are having condensation and we are having evaporation in this heat exchanger, then we are we are saying this is a condenser or this is an evaporator, but it's nothing special. Just for you to know, condensing is taking place, evaporation is taking place to have high density of energy and to be able to work with not too high temperatures or too low temperatures. Okay, very nice. Let's continue into a cooling unit that we are going to use today, and it's the cooling unit we use for our solar cold rooms. This cooling unit is just is a heat pump. It uses R600A, an environmental friendly refrigerant, and you see here also a compressor, right? And I would like to ask yourself, where is the condenser here and the evaporator? Yeah, the condenser is now outside, so you can see here this heat exchanger, right, with a fan. So this is the condenser, and the evaporator will be inside. Is this, in this case, is a plate, an evaporator plate. This is like a fridge without the isolated box, so to say. Yeah, but it's a heat pump, and we use it because it allows local production, assembly, modularity, so on. It is transported in a very compact way. Yeah, it can run without batteries. It uses the refrigerant, natural refrigerant, and it's suitable for thermal storage. And this is very nice because if we put this evaporator plate inside water, then we can produce ice around the evaporator plate. So it's very nice that it's a plate because we can immerse it in water. And now I would like to show you a video of this. If we will be in presential, we could have a look to the machine directly. But now I'd like to show you a video of this. Let's see if this works. You see already the compressor here. Yes, and then the compressor has an outlet. You see here, we have the compressor vapor going on here. Into this pipe. If you can follow, this pipe is going to the condenser. So this is the compressed vapor from the compressor, let's say at 50 degrees. And then we are releasing the heat. We are cooling down this refrigerant, this vapor, with the ambient air, right? That's why we have a fan. And then the temperature is decreasing down to 45 degrees. And at some time it is condensing. So we'll have here condensed liquid coming out of the condenser. Let's have a look here. This is the outlet of the condenser. Then it is going here to our capillary tube, which is in this case the expansion valve. So we are expanding the liquid over the capillary tube, which is inside this pipe and ending in the evaporator plate. Let's have a look here. You can see it. Can you see it? There the liquid is expanding. So it has a lot of space and then it starts to evaporate, producing cooling energy, going up and down in the evaporator plate. And then at some time coming back as vapor again here, going back to the compressor. So here we have been able to recognize all parts of a heat pump and then going back to the compressor. So this is a closed cycle, so to say. Okay, so now we had a look to the different parts. As review, let me stop the video at this case. Compressor, condenser, the expansion valve is a capillary tube where the evaporator, the liquid, so to say, goes through and release pressure, and then the evaporator where this liquid gets into vapor. And now I tell you this machine is controlled by itself. Yeah, the pressures are controlled by itself. Why? If, for example, the condenser is not able to condense the refrigerant, it's because the pressure is not enough to condense the refrigerant. Then we'll have vapor trying to go through the capillary tube, and this is not possible, yeah, because such a long capillary tube, you'll have too much pressure drop, so only liquid can go through it. That's why the compressor will keep on compressing until it gets the right pressure, right temperature, that we get liquid here at the condenser. And then when we have liquid, it can go through. What's happened now if the ambient temperature is higher? We don't have 40 degrees, we had 45 degrees. Then what's happened? Then we don't have condensation anymore. So the compressor has to compress, and compress more to get into the condensing phase. And this happens automatically. And then what are we going to happen? Depending on the ambient temperature and the cooling temperature, we will have a higher or lower pressure difference. Yes, you understand this? I hope yes. The higher the ambient temperature is, the higher the pressure will have to be. The lower the cooling temperature has to be, the lower the pressure will be. So if we have high ambient temperature and very low cooling temperature, we have a high pressure difference. This means the compressor has to work more to get the same, right? Lower ambient temperature, higher cooling temperature, lower pressure difference. The compressor has to work less to have the same cooling effect. You see, the compressor is helping us to get into the two different pressure levels. The cooling energy is coming always from the ambient. That's why a heat pump. And that's why the efficiency of a cooling system is not the efficiency of the compressor. The efficiency of the cooling system is how well we can pump the cooling energy from the ambient inside the room. Let's have a look to this. The concept of a coefficient of performance. You can see it here. The efficiency of refrigeration systems is measured under the coefficient of performance. It is not called efficiency because efficiency, it is related to transforming energy or generating energy. But we are not generating energy. We are pumping energy, right? We are pumping heat. That's why the coefficient of performance is the ratio between COP is equal of cooling power. So this is the Q, the amount of cooling energy that we were able to pump from the outside into the inside, divided by the electrical power, the invested power. Okay, so if we have here, we have let's say 1 kilowatt hour energy use, yeah, electricity use, and we get 1 kilowatt hour of cooling energy. Sorry, kilowatt hour. This is what? Then we'll have a COP of 1, right? But if we get 2 kilowatts hour out of the heat pump of 1 kilowatt hour electricity, then we'll have a COP of 2. Okay, so you see how big the COP is depends a lot on how low the pressure differences are. If the ambient temperature is closer to the cooling temperature, then the pressures are low. The cooling unit will be, the compressor doesn't have to compress so much, will have a high COP. If we have a high difference between pressures and temperatures, then the COP will be lower, okay? So now I think you are coming to the point. COP can be higher than 1 or lower than 1. We don't know it yet, right? But it is clear now that it could be higher than 1 because we are pumping the cooling, we are pumping cooling energy. So it depends how well we can compress, right? How well we run the cycle. How can we know this? We can know this by somebody that spent a lot of time to figure out what is the maximum COP that we can get. So this was a French engineer by name Carnot. Yeah, 1824, he was developing the theory of heat pumps. Very nice. You can find it on the internet or in scientific journals. He calculates the maximum COP that we can get into with a refrigeration system. Yeah, and this is very nice because the equation is really simple. Yeah, you see here the temperature warm, you see here the temperature cold. You just need to have them in Kelvin, and then you enter them in this equation and you get the maximum COP you can get. COP ideal, COP Carnot. Okay, And I can tell you, this COP Carnot will be always higher than the one we have in reality, our COP. And this depends on the ideality factor of our heating systems, yeah, or our cooling systems, sorry. And I can tell you heat pumps goes between 20 and 30% of the ideal COP. So if Carnot is telling us we can get a COP of 10, yeah, and then we have a 25% of ideality factor, then our COP, the real one, will be 2.5, yeah. We will invest 1 kilowatt hour electricity and get 2.5 kilowatts hour electricity. But this depends a lot on the temperatures. If the delta temperature is low, COP will be high. If the delta temperature is high, then the COP will be low. And then we need to understand this, and this is done by the COP ideal. So here you have an equation to calculate your COP based on the warm temperature and on the cold temperature. And now I would like to repeat the question related to the efficiency of the cooling units. So let's go ahead for that. Please vote again. Remember what we answered before. Now answer again. I hope I was able to convince you. Go ahead and answer to the question. Can the coefficient of operation of cooling units be higher than 100%? First answer, yes, even much higher, up to 400%. Yes. Second answer, yes, but not yes, but only a bit higher than 100. Third answer, about 90%, but no higher. Fourth answer, not at all, always below 100%. Not everybody has answered yet. Many people are thinking about it because they might have answered something else before. Keep on voting, please. Okay, so everybody has answered already. Thank you so much for that. Can you see the results? Now it has changed a little bit, yeah, or I will say quite a lot, because if you remember from before, the most voted one was not at all, always below 100%. And now before we used to have 60% on this one, on let me put it here. Before we used to have 60% on the last one, and now we only have 30%, and now we have 55% in the first one. So now actually most of you think that the COP can be higher than 1, and the half of you think that it can be up to 400%. Okay, so very nice. We are getting into there, but I see still 30% of you thinks that the efficiency cannot go higher than 100%. And now my job is in the next slide to try to convince you that it's actually possible, and not only possible, you will see almost at any time we'll have a higher efficiency than 100%, a higher COP than 1. Why? Because Carnot told us it is possible. You are pumping heat. It is possible to get, if you are, for example, having an ambient of 20 degrees here, 20 degrees ambient, cooling temperature 4 degrees. So imagine a refrigerator in a room working. Carnot is telling us, and you can use the equation of Carnot to get into there. He is telling us your COP can get up to 17. Wow. I invest 1 kilowatt hour electricity and get 17 kilowatts hour cooling energy. Amazing, isn't it? Yeah, this is what Carnot is telling us. What about at 40 degrees? It goes to then 7.7. Yeah, a little bit lower. What about if I go to minus 10 degrees? So from 40 degrees to minus 10 degrees. Carnot is telling, hey, with the equation of Carnot, which is the maximum you can get, is still 5.3. So 500. invest 1 kilowatt hour and get 5 kilowatt hour cooling energy. But remember, this is the ideal COP, so the maximum. And I told you to get to the real one, we use the ideality factor that is around 25%, at least for our self-chill cooling unit. Yeah, it's 25%. This means, and I'm going to show you real measurements. Yeah, we measure the energy consumption here, and we measure the cooling energy that was delivered by the evaporator plate. And I tell you, at 20 degrees ambient temperature, 4 degrees cooling temperature, we get 2.6, 260. 40 degrees ambient temperature, we are still at 1.8. I invest 1 kilowatt hour electricity, I get 1.8, 180%. And even if we are producing ice at minus 10 degrees and the ambient temperature is 40 degrees, we are still working above 1. You see, 110%. I invest 1 kilowatt hour electricity and get 1.1 kilowatts hour thermal energy, cooling energy. So almost always our cooling unit works with a COP almost always above 1. Yes, I hope I was able to convince you these were real measurements. The reason is because the cooling energy is coming from the ambient. So the hot ambient is providing here cooling unit, cooling energy, sorry, that can be delivered here at the evaporator. And the energy of the compressor is just helping us to transport this energy, to pump this energy. So let's have a repetition again of this question. Please vote again. If you are still not convinced, then yeah, it's free lunch, isn't it? Let me see if I can again start it. Okay. Thank you very much, Anna. Please vote again.
Yeah, it's important to comment also that the values that you see in the tables that Victor was showing, there need to be multiplied by 100. So there you will get this percentage.
Okay. Okay, we are getting there. This is like politics, right? You just need to talk a lot about something until it becomes true, right? This is what politicians do, but this is really something we can demonstrate that the COP can be above 1, and I am very happy that most of you are now realizing that the COP, the efficiency of a cooling system, can be higher than 1, can be higher than 100%, even 200%, 260%, as we can see here, up to 400%. I can tell you, let us have it here, the answers. I can tell you that air conditioning, for example, quite often work at an efficiency of 400%, yeah? Why? Because the ambient temperature, for example, at night is only 25 degrees or 30 degrees, and the cooling is happening at 15 degrees or 20 degrees. So the delta T is so small that the compressor doesn't have to work so much, so that the COP goes higher up to 4. So it is possible to be at 400% cooling with a cooling system. And this is very, very nice, because it is not only solar energy, right? Actually, you are understanding now that we are using the solar energy to get the cooling energy from the ambient, right? And that's why we get access to such a higher efficiency, to such higher COPs. I am aware there are 2 persons here that are still convinced that it's not possible, that the efficiency has to be always under 100%. And for these 2 participants, if they want to say something, you can raise your hand and we can provide you the possibility to comment on this. That's why we don't call it efficiency, we call it coefficient of performance, because actually the efficiency of the cooling of the heat pump will be, in this case, this ideality factor, right? This 25%. The compressor has an efficiency, yeah? You have electricity and then compressed energy, yes, below 100%. The fan has an efficiency always below 100%, but because we are pumping energy, we are not creating energy, right? This is not a creation of cooling energy. This is pumping energy. That's why we can deal with coefficient of operations higher than 100%. This is very important that is clear for you. It is important that you know the COP is very important, because if you are working with a COP of 1.8 or a COP of 2.6, so 180% or 260%, this is going to affect your design a lot, right? Because you need always less electricity for the same cooling, right? This means you always need to consider not only the amount of electricity you get from the sun, but also how well you can transform this electricity into cooling energy. And that's why the ambient temperature is so important for the design of cooling systems. You can actually have a location with low radiation, but if the temperature is low also, then your design will be cost efficient, so to say. But you might have a location with a lot of solar radiation, but high ambient temperature, and then you also need a lot of PV because your COP is low. So I hope this is understood, because this is so much essential for the design of solar power cooling systems. This can bring me to a point that is very interesting. So if we understand that at heat pump, let's say our cooling unit can produce ice at 0 degrees, as you can see here, at 0 degrees, can produce ice at 0 degrees, ambient temperature 30 degrees with a coefficient of operation of 200%. This is a reality. This is a measurement. This is happening. This is because we are pumping the heat. And we have a PV panel with an efficiency of 17%. Then with a solar cooling system, we are able to transform solar radiation, yeah, let's say here solar radiation, with an energy transformation rate of 34%. So the PV panel can transform solar radiation, 100% solar radiation into 17% electricity, right? But our heat pump can transform 17%, or let's put it like this, 100 watt solar radiation, 100 watt solar radiation, let's have it here, 100 watts solar radiation convert into 17 watts electricity. And with the heat pump are converted into 74 watts of cooling energy. This is wonderful. This means 34% of the solar radiation is converted into ice. Imagine how good this is. Yeah, this is about 1/3 of the solar radiation we can convert into cooling energy. And this is really amazing, and it's making solar cooling very interesting, very efficient with vapor compression heat pumps. And because PV panels has decreased the cost so much, it is also a very cost-efficient way of doing cooling. So in the next slides, we are going to have a look to the components. You have seen already a heat pump, you have seen the PV panels, but what else do we need? So if we, for example, take a conventional heat pump, so imagine we are using just a conventional air conditioner for our cold room or for any kind of cooling system, then we might have an AC compressor. And if we have an AC compressor As you know, we need an inverter to be able to run the AC compressor at 220 volts, AC current, 50 hertz, and be able to provide that with DC current. So if we have, for example, here 2 batteries at 24 volts, then we have here DC current, and we convert it into AC. I think this is well known by all of you. So we might need an inverter. We will need for sure an charge controller, an MPP tracker, our PV panels and batteries. So this is a typical solar system, right? What's the problem of using conventional heat pumps with AC compressor? The problem is you might have a start current that is much higher than the nominal current, as you can see here. So this is the current. And this is then, once you are starting the compressor, you get here a peak of current. And if this peak current is higher than the peak current that your inverter can deal with, then this is not going to work. So always when you are connecting a AC heat pump with an inverter, with a solar system, you need to take care that the peak current is not so high so that your inverter is going to work. Otherwise, you will need a bigger inverter, which at the end of the day will cost you money. Yeah. So even though conventional heat pumps are cheap and are available in the market and so on, but then you will invest your money here in their inverter. And you will invest your money also in the batteries, because the efficiency might not be the best one, and also because you cannot store energy at night. So you need somehow to use the energy from the PV panels to be stored in the batteries for delivering cooling energy at night. What else can we do here? We could use a DC compressor. Yeah. This would allow us to get rid of the inverter, right? This will save us money here. DC compressors, DC heat pumps are normally a little bit more expensive, but then you save also a lot of money in the inverter. Yeah, that's why we use DC compressors, DC cooling units, because we don't want to have to deal with an inverter for our cooling systems. What else? You can even use a DC direct drive compressor. What does it mean? It means you can run your compressor, you can run your cooling unit, your heat pump, even without the use of batteries. So in this case, we don't have batteries, and we can run, we even don't need charge controller and so on, and could run the cooling units with directly PV panels. Our cooling units can do both. They can run with batteries, or they can also run totally without batteries, which might be for some cases an advantage. Let's have a look how it looks like if we have here a look to this diagram. So we see here the power, electricity power. This is the solar energy, right? Here, the solar energy during the day. If we have an AC heat pump, as you can see here, AC refrigeration unit. So every time I'm talking about a heat pump, I am talking about a refrigeration unit or about a cooling unit. It's all the same, right? Okay. So if we have a heat pump like this, we need the inverter, as we just mentioned. We need big batteries for the night, because we need to store the solar energy from the day to the night, as you can see here. What's happened if we have no batteries at all? Yeah, let's think about, we have direct drive heat pumps, compressors that can run on direct drive. We don't have batteries. Now we have an ice storage, a thermal storage. You can see it here. Then from the thermal storage, we will run the cold water inside the cold room to generate cold air. This is clear. Okay, this sounds at the beginning very nice, right? You don't have inverter, you don't have a charge controller, you don't have batteries at all. So it sounds very good, but it has a disadvantage. The disadvantage is that your time where you consume energy is limited, right? It's only limited here for a couple of hours per day. This is normally a time of around 7 hours. So Your compressor can only work during 7 hours because since you don't have batteries, you need the solar radiation need to be enough to start the compressor. Okay, so here's the compressor consumption. And then you have here a lot of energy that is lost, right? You cannot save in batteries. The compressor cannot go higher with the power, and then you have this loss of energy. So our suggestion is to have a mixture of both. Our suggestion is to go to systems that have a mixture of small batteries and thermal storage. This is a very interesting strategy that we follow because the batteries are only there to store the surplus of the day and to extend the hours of operation of the compressors, of the heat pumps, yeah, of the cooling units. For doing this, we decrease the speed of the compressor so that we can run even more efficient, and we can extend the operation up to +7 hours more. Yeah, it could be also more, but normally our systems are working between 14 and 16 hours per day. Yeah, and during this time, they are producing ice. 16 hours per day, they are producing ice from the solar during the day from the PV panels, during night from the small batteries. They are here producing ice, and then we have a water pump and a heat exchanger that is pumping the cold water in the heat exchanger, and with the fan is producing cold air. So you see here, getting the cold air, the cold water. So as long as you have ice, as long as you have cold water, you can deliver cooling energy. Even though the compressors are off, as you can see here, for between 6-8 hours per day, the compressors are not working at all. But we can still deliver cooling energy through the thermal storage, through the ice storage. By the way, this ice storage here that you can see in this diagram is this box here. Yes? Okay. So let's continue with this concept. Let's have a look how it looks in reality. So here you see the insulated room here on the left. This is the cold room itself. Here we get cold water, and here we get cold air out of the heat exchanger. Okay, let's put it like this. You see here the thermal storage, the ice storage. You see here ice at 0 degrees, right? Then you see the cooling units here. I can tell you we have here 1, 2, 3, and then we have also cooling units on the back, 4, 5, 7. 4, 5, 6. If we need more cooling capacity, then we can have more or less cooling units. So our cold rooms normally work with an amount of cooling units between 2 cooling units and 8 cooling units. And with this, we can have a range of 10 to 35 cubic meters cold room, so to say. So we have here 0 degrees, water at 0 degrees going inside the cold room. We have here then water at around 2 degrees. And then we deliver a cold air at around 4 degrees, so that the temperature at the cold room can be around 5 to 6 degrees. This is our minimum, but this is a design, right? If you want to have the cold room temperature a little bit higher, then you need less cooling energy, you need less cooling units, you need less PV panels. So I'm providing here you an example for a 20 cubic meters cold room. This has an ice storage of 300 kg ice, 6 cooling units, around 3 kilowatt peak PV panels, and the battery capacity is around 1000 amperes hours. We have a water pump and a heat exchanger that consume both in total around 40 watts electricity. Okay. To design this, we will learn in the next webinar, in the next session. We will deal with the equations, and today I will give you the first overview at the end of this afternoon session. We'll give you an overview, but if you want to learn how to design such a cold room under the SurfSeal concept, then please don't miss the next webinar. Now let's keep on learning how the system looked like so that you can have a good overview of the different components. Let's have a look here again how it works. So here we have our cooling unit. So this is the ice storage here in the middle. We have the cooling units, and they can run here with PV panels with or without batteries. This is always a design decision that we will deal with also in the next session. But we actually don't need batteries. Normally we install the small batteries, and this system we call the primary system. Primary system. Why? Because this is providing energy to our heat pumps to produce ice. And then we have here a secondary system. You see it here, PV panel, charge controller. And here we always need a battery because this system is providing energy, as you can see here, to the water pump and also to the heat exchanger, to the fan coil. Okay, so why do we need here always battery? The reason is because at night we want to provide cooling energy, even though the compressors don't work. So we need always a battery, and this secondary system is designed in a different way than the primary system. The primary system doesn't have to have batteries, and the batteries can be small. For the secondary system, the batteries are needed and they have to be well designed so that we have good autonomy days. But I tell you already, the energy consumption of the secondary system is maximum 40 watts per day, I mean all over the day. And in the primary system, we are dealing with much more power, so more or less 550 watts for 6 cooling units. So the primary system is always bigger, of course, to generate the cooling energy. Let's have a look here under this diagram. Let's try to find all components there. Let us start with a primary systems. So we see here PV panels primary system. We have 3 cooling units with the first primary system. So these 3, these are providing energy through one charge controller. They are providing energy to these 3 cooling units, right? Okay, then we have a primary system 2, because we have here 2 primary systems in this system. So the second primary system has another charge controller and is delivering energy here to the compressors on this side. And you see here another charge controller is not utilized in this one, but it depends how many cooling units you have, right? Because the system is modular. Okay, and then we have these 2 PV panels here on top that are still missing. These ones are for the secondary system, right? So you see here, secondary system. They have also their own charge controller, and then they deliver energy to the water pump and to the heat exchanger inside. You see the cold cell, the room here with the door. You see here the charge controllers. You see the cooling units. This is the water chiller. Water chiller is for us the ice storage. Yeah. So we have here the ice. And then the cold water is a pump inside the cold room. Then we have batteries for the primary, secondary, and for the 2 primary systems and for the secondary system. The primary system, as I told you, they are not necessary, but we normally installed small batteries for the primary system too, because of the mentioned reasons before. Please, if there is any question for the things that I'm presenting, please don't hesitate to write it on the chat. I'm ready at any time to answer any question. And if you want also to say something, please hands up, and we will let your sound come through. Let's have a look in more detail how a primary system is connected. So now we have here a primary system with 2 cooling units, 2 batteries, 2 PV panels, and a charge controller. So very simple. It's like a solar home system. By the end of the day, PV panels and batteries are connected to the charge controller. Then we have a battery protect because we use Victron charge controllers. And then we have the 2 cooling units that have a thermostat. the thermostat of the cooling units are to control the ice inside the water chiller. So you see here the water chiller from the top, the thermal storage, and this is the ice. I don't know, I hope you can recognize it. These ice blocks around the evaporator plates. Yeah, this is everything ice. Yeah, and the rest is cold water. So for example, here I see water. Yeah, so we have always a mixture of water and ice, and the primary system is providing energy to the cooling units, and the cooling units are running as long as the temperature goes to -5 degrees. You see here the set point of the thermostat of the cooling units. Why? Because imagine this cooling unit, it has a temperature sensor here in the evaporator plate. When we get here to -5 degrees, it's because we have already a huge amount of ice, and then we can stop the cooling units, right? And this is the reason why we have thermostats on the cooling units, because we don't want to overfreeze the thermal storage. Once the thermal storage is full with ice, then we can stop the cooling units.
Sorry, Victor, there is one question. What does dirt have against the condenser?
Well, the system is quite robust in terms, so if we have here some dust or dirt, it doesn't affect so much the water, because at the end of the day here we are freezing and melting the water. We recommend always the water to be clean. For some reason, if you get like microorganisms in the water, then it might develop bacteria that might cause corrosion on the pipes and so on. But this water chiller is anyways closed, so the whole system is closed. As you could see here, this is a closed circuit. The water is going from the water chiller through the water pump to the fan coil and coming back. The water chiller is closed, so normally this water doesn't get dirty. So if you get clean water inside, then it stays for always. Yeah, sometimes you have to introduce a little bit more of water, but I will say here this is not critical. Thank you for the question. Okay, so we understood here we have thermostats that are stopping the cooling units when the ice storage is full, yeah, because we don't want to overfreeze the whole water chiller. Okay, let's go ahead. Now let's have a look to the secondary system. The secondary system is a separated solar system with PV panels, charge controller, and batteries, and then we connect there a fan. Yeah, it's the fan here in the heat exchanger, inside the heat exchanger that delivers cold air. We have the water pump, and then we have also a thermostat. But this thermostat is not in the water chiller. This thermostat is inside the cold room, right? Why? Because this thermostat is stopping the fan and the pump once the set point temperature has been achieved. So if you, for example, want to have here 10 degrees, here you are getting cold air at 5 degrees. Once the cold room temperature is below 10 degrees, the thermostat will stop the circuit, and then the fan and the water pump will stop. Yeah, this is how we control the system. From the one side, we control the cooling units. From the other side, we control the water pump and the fan, the heat exchanger. If there is any question regarding how the system works, or here regarding the wiring diagrams, please let us know. And now let you know the research that has been done in Nigeria since, I will say, 2019. So now for the last 3 years at NISPRI, yeah, there is this a cold room that has been locally produced by Mr. Engineer Adebiji Adebayo, that is today with us, has been the contact person with us and the link to NISPRI, to the Nigerian Stored Product Research Institute. And this has been the person that has been coordinated the research on self-chill cooling systems in Nigeria, also in collaboration with the company EcoTutu, that is the distributor in the country. So we have here some pictures how this cold room works with 2 cooling units that you see here. So this is the cooling units. Here you see the water chiller, yes, and then the pipes going inside the cold room. Here's the heat exchanger for the cold air. Yeah, and here you can see the experiments that has been going on, chilling tomatoes inside the cold room. This was our first activities in Nigeria. In the meantime, we have also other ones and also in other countries. And what is very interesting now that you have seen the technology is to see how easy it is to produce it locally. And this has an implication in the cost. Excuse me. This has an implication in the cost because if you have a finalized system, as you can see here, then you have to import a lot of components into the country, right? Then you have a lot of transport and you have a lot of import costs. So finalized systems are quite expensive compared to local assembly systems. You could also do the assembly locally, but the most interesting is to have the components, self-chill components, to be installed locally with local source material. So then the self-chill components remain low with the cost, also with transport and import costs is low. Then you have your local source materials, perhaps some engineering, also for the local design, for the local assembly, for the installation and so on. But you are able to decrease a lot the price of the technology. That's why the self-chill approach is very cost efficient. And here the company EcoTutu together with NISPRI has done great efforts to be able to produce solar power cold rooms made in Nigeria, which are, as you can see here, normally half of the price of a finalized system being imported in the country. Let's have a look to some examples. This is a cold room installed at cooperative level, 20 cubic meters operating at 10 degrees. Let's have a look here on the components. So you see here on top the PV panels. Then you see here the chart controllers. Here is the water chiller with the cooling units, in this case with 6 cooling units. And then the cold room is here and the water chiller is in this room. With the thermal storage is in that room. This is used for one single product with different seasons because it's as cooperative, so can make access to the business model of getting a higher quality and providing products out of the season. We have another example in another place. This one, I mean, the last one was in Rwanda. This one is in Tanzania. Also 20 cubic meters at farmer level. It's installed at a dairy plant and it stores dairy products. That's why, you know, cheese, yogurt, and so on has to be stored at around 5 to 7 degrees. That's why this cold room is working at this temperature, because in Tanzania, where we are, in the near Dar es Salaam, the ambient temperatures are so high. This cold room has a higher insulation. We are here working with 100 millimeters insulation thickness. You see here the heat exchanger, the PV panels here on top, the cold cell is here, and here you see the ice storage, or you can also see it here. This one has been produced with an IBC container and polystyrene plate. So you see every water chiller, every thermal storage look a little bit different. It depends on the local source materials. And the self-chill installer has always a different way of doing this, as you saw now in these 2 examples. We have another one in Zambia. It's a containerized solution. So self-chill can also be constructed locally as a container, cooling container. You see it here with the PV panels on top. And then half of this container is a cold room. So here is a cold room, and half of it is a kiosk where then cold products can be sold. This is installed in a school. And here you see the water chiller, it is here, and the HR controllers are here with the batteries. We have here 3 cooling units to provide with cooling energy to a cold room of 20 cubic meters, because here the temperature is a little bit higher than in the other case. Okay, let's have a look to another sample. A very interesting example in Kigali, Rwanda, at a marketplace. Because Rwanda has quite low ambient temperatures, here we can work with 6 cooling units at a bigger cold room, 30 cubic meters, 10 degrees. So everything is a question of design. We have 10 PV panels here, 4 for each primary system and 2 for the secondary system. And in this market, farmers can, they usually come in the evening, bring their stuff into the cold room and then pay for 1 day storage. So the business model here is actually to avoiding spoilage overnight or for several days. So short-term storage direct on a marketplace.
What is your view on constructing this system of 20 feet shipping container?
Thank you, Anna. 20 feet shipping container, yeah, no problem. We had this actually already in Mali. You just need an insulated container. And what we did, or what the local distributor in Mali did, is to have a part of the container for the thermal storage, for the ice storage, and the other part of the container for the cold room itself. So similar to what we have seen in the slides. Let me share the slides again. So similar to what we have seen here. So we have here a part of the, because this is also a 20 feet container, so part of the container is like for the, this part of the container is for the water chiller, yeah, for the thermal storage, and then the rest can be used as a cold room, yeah, whether you have an insulated container or you insulate the container from inside, no problem at all. Okay, so another sample, another cold room at a marketplace, 30 cubic meter, 10 degrees. You see here where the water chiller is. The thermal storage is in a separated space, yeah, outside of the cold room. And then we have here a roof and the PV panels here on top and the cold room. Very nice systems. Some sandwich panels, they can be also directly on the rain, so there's not a problem because they are waterproof, right, from inside and outside. So this is quite easy to build. Remote monitoring is a very important question to deal with, and very important because at the end of the day you need to see what's going on with the temperature outside and temperature inside. Yeah, I'm keeping the 10 degrees, as you can see here. So we are here for 1 month below, for 1 week, sorry, below 10 degrees. But sometimes, for some reason, many products are enter inside the cold room and then the temperature is increasing. So we need to know what's happening there to be sure that the quality of the product is good, and also to avoid any failure. So we had, for example, a couple of weeks ago, a system where the water pump was not working well, and we could discover that very good with the remote monitoring and be able to replace it on time before we had a total failure of the system, so to say. So that's very important, remote monitoring. And now I come to a cold room from Ekotutu in Benin City in Nigeria. Constructed with a water chiller with 3 cooling units. That is that was using the insulation of a broken refrigerator. So this is also an opportunity to recycle products, have a circular economy, and so on. So here you see pictures of the cold room with the heat exchanger delivering the cold air. And what is very exciting is what is coming next. We are at the moment planning with our distributor in Nigeria, the company Ecotutu, and under the research of NISPRI, planning a new cold room at Mile 12 International Market in Lagos. And this is going to be installed in the next weeks, so that in the next webinar, we will have a look to that, and we will have inauguration activities there, promotional activities, and during the face-to-face training, we will be able also to visit this cold room on the days after the training.
Yes, I would like to mention thank you for this introduction to these activities that we are having in Nigeria. And from there is one question about what is the possibility of having self-chill system install a cargo export port location for fresh vegetable export, like 50 cubic meter size. Example in agro cargo ports.
Thank you for the question. I think this shouldn't be a big problem, yeah, because as you know, our technology is scalable. It can be adapted to different systems, so the size of the chamber wouldn't be a problem. We will just need to have a look to the temperature that is needed, and then doing the design accordingly. We had recently also an example of a container that needed to be cooled down, but the solar surface was limited, right? And then there you have the problem. Sometimes you cannot achieve, or you cannot get to the design to get the temperature you want to the available surface, right? Some containerized solutions need to have or only have available the surface of the container itself. So it is a design question, but as long as the solar surface is enough available, so to say, there should not be a problem for that. And we have learned that the business models around the exports produce is very big, because sometimes the products are waiting for very long there. And normally there are bigger cooling facilities there, but there will be also a chance for self-chill cooling systems to be installed there.
Thank you very much, Victor. And there is also another question. Maybe we can recap a bit on the water chiller and from the primary system. And there is a need of a bit of more explanation on that before we continue. Maybe you can give more insight on the diagram.
Yes, it's my pleasure. We can start from here. So you remember we have the cooling units that are producing ice. From solar energy, we are producing ice. So we have here an ice storage or water chiller, right? So it's the same because we are cooling down water, right? Water chiller. And then from the ice here inside the water chiller, we deliver cold water when we need it inside the cold room, where we have a fan coil delivering cold air. And here you can see it quite well. So you have here your cooling units, your ice. So this is your water chiller. Then the cold water is going here up to inside the cold room, coming here, cold water, and then you get cold air. So this is how it works. And the wiring diagrams were described here, yeah, how the PV panels are connected to charge controllers, batteries, delivering energy to the cooling units. And here you see what's happened inside the water chiller, right? So you have the evaporator plates of the cooling units. They produce cooling energy, and as soon as you get to 0 degrees, because they are immersed in water, they start to produce ice around the evaporator plate, right? And this is what makes you be able to have an ice storage system. And then the cold water, so we saw here, this is ice, 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 Like around every evaporator plate, we have ice. Perhaps you cannot recognize it in the picture. And the rest is water. Yeah. So water, ice, ice, ice. You have here some water. And then you get from the bottom of the water chiller, you get cold water that you pump inside the cold room. So this is the working principle. So that you have a separated solar system, secondary system with your fan and your pump and with a thermostat, so that always when you need cooling energy, when you enter products or when the temperature is above your set point, you pump the cold water of the water chiller to produce the cold air. Please confirm us this has been now understood, the working principle. We are waiting to your answer. Okay, if there are other questions in between.
Yes. Yeah, Adede, maybe you can reply us.
Yeah.
Wonderful. Thank you.
Thank you very much. That's nice. And thank you for reminding, right? If you haven't understood any part, it is not your fault. It's my fault, because now you have seen it was explained a little bit slower and now it is understood. And we are here today to come together and to understand how a self-chilled solar cooling system works. By the way, let's have a look if we are all together. We have 26 participants at the moment, and I will really like to know. Hold on, yeah, thank you. I would really like to know if we are all listening. Please answer. Just give us the feeling. Anna and me, we are sitting here, both of us, one in front of the other in a small office at Solar Cooling Engineering, Germany, which is, by the way, just close to the company Faesan, that is the German distributor of self-chill components. Okay, thank you very much. Everybody's there. This is really good news. Thanks so much for keeping it awake. And now let's continue. So we had a look to the different samples, cold rooms. We announced what is going to happen next in Nigeria. We are very excited. This is going to be the first EcoTutu cold room at a marketplace with self-chill technology. We are very proud of EcoTutu, of their progress, and we are very proud of counting with the researchers of the Nigerian Store Product Research Institute in Ilorin. But there is another question.
Yes, there is another question about the cold water that goes into the cooling chamber is in the water form, droplets or mist. What change it to vapor in the cooling chamber?
Okay, there is this question, yeah. What we have here in the water chiller is really water, yeah, just water and nothing else. Don't confuse it with the refrigerant inside the cooling units, right? So the cooling units, they have a closed circuit. Let's have a look here to the cooling unit itself. It has a closed circuit, so we have here evaporator and condenser, but the refrigerant is inside, right? So we are producing cooling energy at this evaporator plate. And then this evaporator plate is in contact with water inside the water chiller, and then is producing ice. And this ice is freezing, then melting, and so on. So freezing during the day, melting at night. And the cold water is used to be pumped inside the cold room. I hope this has been understood. Please let us know if this solves your question, or if there are any questions. We prefer to solve them on the fly. So the refrigerant of the cooling units is inside the cooling units, inside the heat pumps, and the cooling medium is the water. Yeah, is the so Don't confuse it. We have a refrigerant, but we have also water that is then being pumped inside the cold room. Just normal water, nothing else. There's another question.
Yes, and as Victor was commenting, this water is just served in the heat exchanger. So we are having a secondary cooling system, let's say, in order to extract the heat from the material that is placed inside of the cold room. So there is, I hope that Cecilia, we answer your question. If not, please, you can write in the chat whether we can clarify your with our answer.
Okay, we are getting into solar cooling experts, self-chill experts, and need to assure that we have thought on everything. So if you remember this slide from the beginning, what are the key considerations for the success of a solar power cold room? Yeah, let's have a look what we have reviewed already. So we have been talking about business models and agricultural produce. We have been talking about the location and how important it is to have the to be aware of the ambient temperature and the weather conditions. We'll have a look to that closer on the next session. We have having a look on the different types of cold storage. So with technology we can use, I have been telling you about using vapor compression heat pumps, cooling units with thermal storage, with PV, and so on. So we have a clear picture how a solar power cold room can work and then their self-chill approach. And what we need to consider is the estimation of the cooling demand and how the power supply is going to be done. I'm going to give you an overview on how this process needs to happen, because this is very important to know to design the system. We need to know how much cooling power we need, what is the cooling demand that we have to be able to develop the whole cooling system, right? So to summarize this, the business model determines the temperature I want to have in the cold room and also the size of the cold room, right? So then the type of cold room itself will determine how the components need to work with each other. So if we are working with self-chill cooling systems, we have a thermal storage, ice storage. And then based on this, we can go directly into the estimation of the cooling demand. Let's have a look what is important here. We'll have a look to the rest of things also during the next webinar, but now let's concentrate in this one. So we have here the design process, how to design a solar power cold room. So the fresh food storage considerations, yeah, what are the storage conditions? This we have review. A consideration of the insulated structure. So this is the sandwich panel, the insulated room itself. It's very important to know what we are going to use there so that we can design what is going to be the thickness and so on. We need to figure out which cooling systems we are going to use with refrigerants and so on. Here in self-chill, it is clear how it is going to be. Remote monitoring, yes or no. And now we are going deeply into the cooling demand. The cooling demand is coming from cooling the products and thermal losses. Let's have a look to that in the next slides. And then we need to figure out, okay, how many PV panels, how many batteries, do we have a diesel generator, do you have a mini grid, are we going to use the grid, yeah? But this is normally not the case or not needed for self-chill systems. And what we have at self-chill is always thermal storage, yeah? The water chiller is a thermal storage. Okay. First of all, we need to understand when we are putting products inside our cold room, what is going to be the temperature of the products, what is going to be the cooling curve. Let's have an example here. Imagine you have an apple at 30 degrees and you just entering it into the cold room where you have air at 5 degrees. So the question is how fast it's going to be cooled down in the surface here in green, and how fast it's going to be cooled down in the center. So now I have a question to you that will be answered in the here in the chat. Let me have a look. No, I didn't program this one, so you are going to have to answer in the chat, please. So let's go now, for example, for the center. So for the center of the apple, how many hours do you think that will take to be cooled down at 5 degrees? So the air is at 5 degrees. The apple is at 30 degrees. How long do you think it will take until we will be at 5 degrees? So please write on the chat if you think it's going to be half an hour, or you think will be perhaps 1 hour or 2 hours, 3 hours, 4 hours, or whatever you want to write. Please let us know. It's just to make you think about it. We are considering the center of the apple. So what is your feeling? Is it going to take, an apple is quite small, isn't it? So let's try to develop a feeling how fast this is going to happen. Are we going to, is this going to happen spontaneously, or will it take a little bit of time? So the first question there is, we need to know the rate of cooling. Well, the rate of cooling, I'm telling you already, we have air at 5 degrees. And we have always air at 5 degrees. Imagine we have enough cooling power to have always air at 5 degrees going around the apple, which was initially at 30 degrees. So this you have. Just provide your feeling. You cannot do a mistake. I tell you, the first time I was thinking about it, I was also not totally right, but that's why there are equations that we will learn in the next webinar to calculate it ourselves, so that we know how long it takes. But now I really need you to answer there. Yes, there is an empirical model. So we have here a question. Yes, there is a model to calculate this, and we will learn how to calculate this in the next webinar. There is a couple of simple equations that you can use, and we have also an Excel tool that can calculate that for you. And that depends on the size of the fruit or vegetable. It depends on the heat capacity of the fruit or vegetable, and of course on the temperatures, initial temperature and air temperature. Besides, this is a simple model. Now I would like to see if you could more or less from the feeling estimate how long it will take. So Anna has provided you with 4 options. Take a little time to think about it. There is a question here. Ambient temperature is needed? No, because the cold room is at 5 degrees. We have air at 5 degrees. So the apple is coming at 30 degrees inside the cold room, and then the ambient temperature doesn't matter. This is the job of the cooling system itself. So now imagine an apple inside the cold room at 5 degrees. Yeah, imagine a simple apple inside at 5 degrees. So now, thank you, Anna. She was able to program this question for you so that you will be able to answer to it directly. Please vote. Now we really need your answers. And this is important because these kind of questions are rising our mind and are making us being figuring out how we can calculate this and so on as preparation for the design process on the next webinar. Okay, very nice. 6 persons have answered, 7. Thank you very much. Keep on voting. So the apple is in the middle of the cold room at 5 degrees. How fast it is going to cool down? This is small apple. how fast will take the center of the apple to be from 30 degrees from the beginning to 5 degrees. So we are almost done. I'll share the results. So 60% of the participants voted. Not yet. Can you see it now? 60% of the participants of you answer the question with 2 hours. So most of you 2 hours, then 30% 30 minutes. So 90% of you have the feeling that the center of the apple will be in less than 2 hours at 5 degrees. And now we took the equations for you that we will share in the next webinar and calculated this to see what's happened there. And these are the results. The results show us that the center of the apple is not even feeling the coolness in the first hour. Can you see it here? Yeah, it took almost more than 5 hours for the center of the apple to be at 5 degrees. And the surface was of course getting colder faster. Here after 2 hours it was at 12 degrees, but the center is still above 20 degrees. And this is what's happened when we don't do calculations. Our feeling is normally a little bit different than what the reality is. And because the cooling curve is so slow, sometimes there is a need to have a faster cooling. So imagine what's happened with bigger products, like here in this case, watermelons or other products that are very big. If you put them in a cold room, it will take so long to cool down, right? They will probably or could have an impact in the quality if the cooling curve is so slow. That's why we might need to go for water cooling, yeah, or a pre-cooling before we go into the cold room. There are cold rooms that, for example, have a pre-cooling process. Yeah, they have, for example, ventilators or a chamber that is colder so that the air is moved very fast at a lower temperature so that the cooling curve is faster. So we need to have this always under our minds, that the cooling speed is also very important. The same, for example, cooling down milk cans or milk inside milk cans in a cold room. It takes ages. The milk will spoil before. Yeah, so it's not only the temperature, it's also how fast we are able to cool down the products. So please remember always this. And next webinar, we will have a look to these equations so that we are always sure that the cooling speed is going to be appropriate for the requirements of the products. What else? Once we know the cooling speed, so we know how fast our produce will cool down, then we can calculate, depending on the amount of products that we have, how much energy we need to cool down this agricultural produce, right? So we call it here heat extracted from the product. So we have here the cold room, the products inside, the cold air, and depending how much products we have, we will have more or less heat extracted from the product. Depending how fast the cooling curve is, how fast the product cools down, then this energy will take place in a shorter or a longer time, which is also important. We need to know if this energy is distributed all over the day, or it is only happening at night, or whenever we enter the products inside the cold room. What else? We have also respiration inside the cold room. This is the energy delivered by the products because they are a living plant, right? So they consume oxygen, emit CO2, and they deliver also energy. So we need to double check every product if the amount of energy they deliver by respiration is considerable or not. I told you already, this is not considerable for every product, only for a couple of them. but we need to always to double check. What else? The thermal losses, right? So imagine we have here outside 35 degrees, and inside we have 10 degrees, and we have an insulation thickness of 100 millimeters. So we can calculate how much thermal losses we have, how much cooling energy get lost, or how much heat energy we get inside, right? So we have already 3 factors, right? 1, 2, and 3. The heat from the products, the respiration of the product, and the thermal losses. These all we need to consider for the design of a cooling system, of a cold room. But this is not all. We have also other things. We have, for example, air infiltration. What about when you open the door? Then you are getting inside the cold room humid, warm air that is going to cause a cooling load inside the cold room. So this needs also to be considered. And what else? What about if we have equipment? If we have equipment inside the cold room, if we have, for example, the fan is consuming, I told you before, 40 watts for both water pump and fan. I can tell you already our fan has consumed 27 watts. So this electricity consumed inside the cold room will have also a cooling demand. The same if persons are going inside the cold room. Every person emit a certain amount of heat energy to the environment, and this needs to consider also for the design of a cold room. Okay, I think we had here everything. Let's have a look here again to our cold room. We have the cooling energy. We have products inside that might have respiration, evaporation. We have here the cooling load of any fan that is inside, of the persons that are inside. This all needs to be considered. Okay, so we are coming to an end. As an introduction, what we will do in the next webinar, we will go through the design process of a cold room like this one. We will figure out, okay, how many products are we entering per day inside the cold room? Is it, for example, going to be 500 kg per day? What is the ambient temperature, the weather conditions, and what is the size of the cold room? And based on this, we will do the calculation of the cooling load. We will have a look to the weather data, so that at the end of the day, we can calculate the results that includes the cooling curve, how fast the products are going to be cooled down. Let's have a look. There is a question, Anna told me.
Sí. Yes. Yeah. As we are moving to the designing toolbox, yeah, maybe we can go through this question from Cecilia. Some of the participants are having solar cooling systems as a thesis, where 50 to 100 kilo capacity. What are the things to consider in the design and calculations?
Yes, that's a very good question to be considered here. Let's close the design of the cold room first, and then have a look how it will be for an ice maker. So for a cold room, we said, okay, the size of the cold room, the amount of products of the cold room, the size and the ambient temperatures are important for the thermal losses. And then the results are the design of PV and batteries, the water chiller, the ice storage. And then if we do an economical calculation, we get the payback period. So in the next webinar, we would like to ask you also to think about the income generation of such a cold room for the different business models. Okay, if we have an ice machine, then what about the cooling demand? The cooling demand is coming directly from the amount of ice that we are generating per day, right? If we have 100 kg ice, then we know the amount of energy that we have to produce for this day. And then we have also thermal losses on the ice machine itself. And then if we know the ambient temperature, we calculate the COP, and based on the COP, we have the amount of electricity that we need. And then we go directly into the calculation of PV panels and batteries. So this is the way of dealing with this, and the way of processing, of designing the system. So it's quite similar, I will say. So this is again an overview of our next webinar, taking place on March, in 2 months. Calculation of cooling curves, calculation of cooling demand, thermal losses, infiltration, cooling the products. So we'll take a lot of time to go inside the equations and so on. Then we'll have a lunch break and design the ice storage, batteries and PV, have a look to the SL design toolbox, and then we will show you other cooling systems that can be done also under the self-seal approach. Thank you very much for your attention. I'm looking forward for the next webinar session to get deep into the equations we need to use. Don't forget your calculator, and yeah, I'm really looking forward for that a webinar session, but also to meet you personally in Nigeria. Thanks so much, and please contact us at any time if any other question rise in the meantime. And at this stage also, thank you very much to Anna, to Nispri, to Dr. Omodara for making this webinar possible today. And of course, all participants. Stay safe and bye-bye.
Thank you, everybody, for supporting us on this webinar, and we hope to see you next session too. And Dr. Omodara, if you would like to make some close remarks.
Okay, so I want to thank Dr. Anna Rogers, Dr. Victor Torres, and all the participants. It's been a wonderful time. I want to believe that is a time worth it. And I want to thank the participants. At least at the peak of the period, we have about 40 participants. Right about now, we have about 30 or thereabout. It's not a bad number. We are hoping that at the end of the whole series, we'll be able to build a formidable team that can champion the application of solar technology in Nigeria. Hopefully, we are going to have a regulated program for the country in the future. So we are sure that we have a group of experts who can make this happen. Let me just say thank you to the team from Germany once again, my colleagues here in Nispri, and every other people, especially people from the private sector. We appreciate your participation. Let's make it a date called March again. We hope our election will go well. It's one of the reasons why we have slated the second webinar for after the presidential election. Hoping that everything works well. We'll see you in March, and it's going to be another wonderful time. Thank you very much.